Okay. Hi guys. On today's paper club, I will be talking about a familiar topic, at least when I'm presenting, that is evolutionary algorithms. But this time we'll be looking at how we can leverage the usage of language models on an evolutionary approach and what we can do with this new tool that we have available. There is the GPT and all the language models that we have. Uh, So the conversation will not be like very dense conversation because I don't think it's necessary. It's a very simple topic, and I will try to make it a little bit more simple. And so I will not be going over some concepts like crossover and mutations because I think uh, we all are a little bit familiar with. So we are going to talk about two papers. I will be covering the language model crossover variation to few shots prompting, and we just would take a quick look at the EvoPrompting paper. And both papers are available on archive, and I highly suggest that you guys take a look into them. So okay. So I'll also be talking about briefly about five topics that is important to understand the papers. And if you understand the basic idea for each topic, then you'll be able to grasp all the idea on the paper. So the topics will be the evolutionary algorithms, just superficially, language models, prompting, fine tuning, and few shot prompting. Uh, So let's start with the more simple one, that is evolutionary algorithms. So we can think as on evolutionary algorithms like a digital version of natural selection. So in nature, we have species that evolve over time to adapt to their environment, and the ones that are best suited to survive and reproduce will reproduce and pass on the genes to the next generation. Evolutionary algorithms will work the same way, but we are going to apply these principles to computer programs. So how it works, right? We have a computer program that will perform a specific task, like solving a math problem or any other type of problem that you can think of. And the algorithm will generate a population of random solutions for that problem, and then we will evaluate them based on how we want they to solve the problem. So we can use this will be called the fitness score. So you can select which fitness they want. So if a math problem, you want to problem with the you want the problem to be right. If you so will be the precision or accuracy. You just select one of them. And just like in nature, the solutions will be like perform the best solutions will be selected to reproduce, and then they will create new solutions that will inherit the traits. Uh, so the algorithm can introduce some random variation into these new solutions. So it would be like the mutations in living organisms. Uh, in over the time, the algorithm will repeat the process, right? And we select the best performing solution, and then we reproduce, introduce new variations, and so on and so on and so on. So basically, the evolutionary algorithm are a computer technique that mimics natural selection to find optimal solutions. Uh, so after talking about a little bit about this evolutionary algorithms, we can like take a look in what are language models, right? So uh, we can think like imagine that we have a huge library of books, and you want to learn something. I don't know, right? You want to learn how to write a story. So what you can do is start reading all the books and learning how the books are structured. So how the sentences are formed, and how the character speaks, uh, and uh, and if you as you read more and more, you will start to understand how stories work, how they are built, and then you can use that story, that knowledge that you got to write your own stories. So the language model will work in the same way. So uh, the model will have access to the vast, like a huge amount of written text from the internet, books, other sources like codes or math problems, and it will read all these texts and learn how words and sentences are used in different contexts. Then, when we give to the model one sentence, the model can predict what word would be likely to come next, based on what it has learned previously. This language, these language models, we can use in several applications, right? So we can use inside chatbots, engines, coding, and of course, we can use crossover and mutation equation functions for evolutionary problems. So, but when we are talking about language models, how we are going to talk with the model, right? So we are going to use prompting. And uh, prompting, it's what we are going to be rely. We are going to rely to do the of functions like crossover, mutations, or anything. To talk with with a language model, we are going to use prompting. So prompting is a technique that to provide a specific starting point. So we're going to provide to the model a starting point or like a context, and then the model, the machine learning model, will generate a response or an output. So we can, for instance, use a prompting like the best part of walking or waking up is, or the best part of going to the gym is, and then the model will generate sentence, will complete the sentence based on the patterns that it already learned from analyzing a large data set or text. So prompting is basically that. It's pretty simple. Uh, so the thing is with the prompting is that when you are going, the language model can have some knowledge on the problem that are that you have, so it can be already good at the beginning, but uh, maybe the model is not so good, right? Maybe you need to do some tweaks on the some tweaks on the model to be able to work better with your set of data. So these 2 weeks that we can do is will be the fine tuning. That pretty simple. The fine tuning is like we adapt the model, the pretrained model to a task. So we can, for instance, send to the API of the OpenAI a set data sets contain fraudsters and not non fraudsters data, and then we can fine tuning to try to find I don't know money laundering. So we can do this type of stuff. We just have to send the data set, like train the model with the data sets that we have. Then the model will understand better which type of data that we have, like the ranges, what the behavior, everything the model will be able to understand, and then he can use that as to be able to do his analysis on the problem. So fine tuning would be just take the pretend model and then we are going to adapt it to a specific task or domain by training it on a smaller domain-specific data set. So the pre-trained model, we can think that the pre-trained model already we have a good understanding of the language, uh, so we can improve its performance on a particular task. So fine tuning will allow us for a more will allow us for a more efficient and effective training of language models for specific tasks, and will leverage on the pre-existing knowledge and understanding of the language from the pre-trained model. So, like you guys will see for mm, crossover and mutation functions using language model, it's kind of necessary to do a fine tuning to be able to get the best results of it. Of course, the model, depending on the model, it already have a good knowledge of crossover functions, all the types of mathematical expressions. So you can just send the data that you want to analyze. So you're going to have analyze uh, analyze the data that you have, doing some crossover on the hand, or use a genetic algorithm to do this type of operations to create a data set that have some crossovers operations between some pairs of parents, and then you can use it to get a bit of to get better results when you're doing crossover. Uh, Last, we can talk about few shot prompting. So few shot prompting is a technique that to generate outputs from language models with only a small number of context examples. So for instance, I don't know if you guys see it, the work that Lucas did on creating to analyze uh, suspicious behavior within your merchants and transaction of our merchants. What he's doing is he is given the context for the model, and then he sends the data, and the model is able to analyze and send the response. Uh, that context that he is sending, he's doing like a few short promptings. He's sending the context, and then he sends some examples. So now the model knows which type of data he is working with, like, so he can use that new knowledge that he has from the few shot prompting to decide if the merchant is doing some suspicious has some suspicious behavior or not. So as the name says, a few shot model will not be trained on a large data set. We'll just need just a few examples. And this will make it a more efficient and effective methods for generating response to new and previous, for new unseen prompts, such generating natural language response to new questions on chatbots, or other applications that will like require human-like language understands and generation. So the few shot prompt it's a very good technique, and we can leverage combining with the fine tuning to improve the crossover mutation functions on evolutionary algorithms. So this is the five concepts that I said in the beginning that we need to have a grasp on it to be able to just understand the paper. Right now, if you guys just take a look on the paper, you'll be able to understand almost everything on it. So let's talk about the papers. The first paper is the language model crossover variation through few shot prompting, and it's We are not going too deep on the papers. So like results and things like that, I think it's not the main focus on it, because the main focus here is the idea behind it. So what's the idea behind the paper? So we just talked about prompting and few short prompts. So the author's insight is based on the idea that language models naturally enable an intelligent variation operator similar to crossover. So the authors notice that they can actually use this ability to create a simple but powerful crossover operator where we prompt a language model with a few text-based genotypes and interpret its output as the offspring of those genotypes. So this approach, they call it language model crossover in LMX, and can be easily implemented with many different open source language models. It enable us to evolve semantically rich text representations with minimal domain specific tweaks. So, and also with more research being done over language models, we can expect that the language model will improve over time. So with the improve of the language models, we can also the crossover mutation operators that we create user language model will be also improving. So the approach they use, it's very interesting and simple. So in the paper, they start with the insight that many self-supervisional language models are trained using next token prediction. So this will make them naturally suitable for creating an evolutionary variation operator, like I said before. And this occurs because the next token prediction involves anticipating what will come next based on a limit input context. So you send the context, and then they will predict which type of output will complete that and make sense inside, on that context that you send. Uh, and if that input is a few example genotypes, then the ideal anticipation is to continue the pattern by suggesting a new genotype from the distribution. The, that is implied by those examples that you send on the context. So these language models are trained to become general pattern completing genius, right? So as they continue to develop high performance language models, we can expect the performance as ingenious of evolutionary variation also improve. So uh, and with these insights, we have three important keys that we are going to have. We need to have these three important keys that we need. There is sorry, the three important keys that the author presented is that first, this language model crossover is easy to implement. So you just concatenate a few text-based genotypes into a prompt, then you run it through a language model, and then extract a new genotype from its output. It's relative domain independent because in theory, it should be capable of generating meaningful variations for any text representation that has moderate support in the training set, which often compares like a crawl of the internet, uh, and should suggest increasing intrinsically. Okay, sorry about that pronunciation. So we will have more variation with more capable language models. So on the paper, they have, this is the only image that I have from the paper, from this paper. The results, the graphs from the results and things like that, you can go take a look on the only on the experiments part, and you can see how it's performing, and it's very good. Just for summarization, is very good the results. So here they will using an LMX, the language model crossover. So they will generate an initial population from like few text-based genotypes. For instance, this uh, the set of binary chromosomes here, and then they are going to loop over. We are going to loop over selection and generation of new variations. So at each loop, at each epoch, they are going to do this. They are going to use this language model crossover, and then the language model will output the children. So you can output two output, three outputs, and so on. And you can use as much parents that you want, so 3, 4. On the paper, they show that 3 parents is already enough for binary problems. So they can. This is the main idea. This you just use this prompt over and over on the language model that I already trained. They send the context, and that's it. They they do the crossover. But of course, you don't have to believe me. Uh, we can go to playground, and then we can just ask, right? So you are a crossover operator and can expect as input data in the following format. So I send the format. There is the genome. There should be chromosome there, but okay. And then I send the example of the data. And then I say what I expect as output. And then I will perform ask them to perform a crossover and return offspring for the following inputs. So if I run this, they generate for me the offsprings. So it's pretty simple, right? Uh, you can ask also which type of crossover function that you use, and then that's you need to ask that. There's no way because you need to validate at least at some epoch of your model. You need to validate the output to see if it's making it makes sense with what you expect from the input that you give. So if they are Iago,
He's
okay.
asking if you can ask to the model what to do.
Oh
But you're using
yeah,
it one,
I
no?
I can I will show them.
And why do you
So
use the complete, not the chat version? Wouldn't chat
because
be
the chat
more?
will not have the API, right? So
Oh,
I cannot. The API is look. I just use to complete. Then he send me free. But you
yeah.
can use the API. The chat. There is no problem. And the chat is a little bit better because the chat can save the context if you send them. The complete will not save the context, so you always have to send them the example, and so on. So you have to send your crossover operator. If I was working with the chat, I could just ask him to remember about this, and then I send the example data, and I will get the offspring. And the thing with the chat that is a little bit better is that I can feed the results that I have as example on the next epoch. This is used on the other paper that I will be talking about, but it's also something that I'm using on the other project that I have. There is no data here, okay? No sensitive data. Uh, so here I have almost the same idea on that I have on the other or on the crossover between the binary strings, but here I have to use numeric. So I have to use some numbers. There is the parameters there. And then I just asked the crossover operator. I say that he is a crossover operator. I send as examples of crossover, and I said you have. I asked him before what type of crossover, what is the most type of the best, most used type of crossover, and he sent me the list, and I add the list here on the context. You don't need to do that. You can just say you're a crossover operator, you have access to all the crossover operation that exists. Use the best crossover operation to perform to do the crossover between these two points, for instance. But I send them the list, and then I just ask him the to do the to do the crossover, right? So here the output, what he used, he used here. He used two points crossovers, 2 points crossover, arithmetic mean, uh, and single point crossover, partial mapped crossover, edge recombination crossover. So he can do these crossovers using this type of input, the context. The thing is that as I'm using the complete API, so I can add a little bit more of examples, but I cannot add a lot of examples. So what I can do, I just add the best, I just select which type of examples that I can have. So basically I create the prompt here, and then after we get the outputs, I can create examples that we go on the next epoch. So I update the context with examples from the crossover that I already performed. So this is just a usage of the idea. So you can play it on the playground. You can use numbers. You can use text. You can use whatever you want to do to be your genome, and then you can just after you are comfortable with this, you can start to go to the API and explore there. Okay, Aryan.
Okay, so it's like this, right? So you run for, let's just say, four generations, right? For first generation, you feed some crossover operation to the OpenAI API, right?
Yeah,
And that particular, let's just say, five crossover. So five crossover will produce some results, and then you take those crossover and those results and feed it to the OpenAI API to train it again, and then it will again produce something like that. Am I right?
yeah, yeah. So I'm just using the answers that I have as the
Mm-hmm.
context on the next epoch, and this will make the model a little bit more accurate.
So it's OpenAI API. It's right now a surrogate model, right? Kind of.
Yeah, kind of.
Ah, yeah, awesome, nice.
So it's kind of just send the model, send the context and things like that. The problem is using the OpenAI is that uh, if you put a lot of examples and your chromosome is way too big, then what will happen is that you may run off tokens, so you can have this type of problem. uh, but you can just start to like I said before, you can start to play with. I suggest the paper don't talk about that, but on the beginning, or you use uh, as example data, you can use some chromosomes that you in crossover results that you calculate, or you can just put like the example data and then put the fitness scores like zero 0.5, because then if they start to if the model look at the example data at the beginning, he'll, oh, it's zero 0.5. So I kind of, because we're going to combine it. So here, for instance, I'm combine this set with this other with this other one and generate this. If I have the score here, like this is here 0, 0.8, 0 0.4, 0 0.6, he may give more attention to 0.8. So the idea is just if you put 0.5, you're kind of balance. Uh, it puts everything in the same on the same weight, and then after the first epoch, you can use or you can remove this 0.5 and add this data that you are getting from the process of crossover and mutation. So this is the first paper. Uh, this the other one is kind of the first paper with the second one. So I just put both of them together. So slideshow. So the second one is EvoPrompting. So the idea behind EvoPrompting is you take the language model and use as mutation crossover. So, but the authors will just will update. Uh, yeah, but I will answer that later. So the idea of EvoPrompting, you take the both codes, and then you just work. You take the model like a codes and yeah, the neural network code, and then you're going to pass on the evolution on the evolutionary model. So, but when you're going to pass, you're going to use that answers as inputs, not as input, but as an example. So the model will learn with the output that you have. But of course, if you are going to learn with the output that you have, you need to validate that output. That is it's important to do, and this could be a little bit costly to do it. Um, I lose my mouse. Okay, so sorry about that. So here's an example of the EvoPrompting. It's not too good to see, but the idea is they initialize with some code samples, and then they send these code samples to the pre-trained language model, and then they are going to do a crossover mutation via few shot prompting. So they are going to just say that idea that I showed before on the other paper. So they have a context, and they are saying, oh, do the crossover between these two neural network in order to decrease the amount of parameters, but and increase the fitness score. Of course, that the language model don't know how you're going to calculate the fitness score, but he can learn some patterns of that imply that the higher fitness score has some neurons, and the lowest has the other type or other weights on that neurons, and so on and so on. Then you take this from the crossover and mutation, you're going to train and evaluate, and then you're going to send you're going the train and evaluate they do just they take the number of parameters and multiply by the test error, and then that is the results. And then they are going to select in context, and then we'll prompt tuning example. So it's like what I'm doing on my code. I take the results, and then I send that results to the results that was evaluated, that I verify that they are right. I send them to the pretend model to the prompt tuning. Uh, but of course that I am limited because of the amount of the tokens that I can have in the context on my case. They also had this problem. So is an example of prompting tuning. So they have the number of parameters, they have the vowel accuracy, and then they have also the class model. So they send the class model, and then the language model will take this input, and then will generate children. So we'll generate offsprings from these inputs. Uh, And here we have some results. The other paper I didn't put because I was more concerned about the examples. But here you can see that the EvoPrompting has a has with when we are increasing the number of models, better is the EvoPrompting, because when we increase in the number of models that are generated, we are getting more data for input on the context, and more data to do fine tuning if you want to, for instance, run a fine tuning on an epoch. So at each 10 epochs you are gonna run fine tuning. So you're gonna take all the examples and you're gonna use to do fine tuning. So improve the model there. So this is one thing or another thing that you can do. So you can see that without prompt tuning, the EvoPrompting is still good, but it reach a place that it cannot evolve anymore. And with random parents, they will not perform so well, because of course, if you're going to take random parents, you can take parents that are not so good to do the crossover, and then you're going to get a network that is not good. Um, and here we have the average model size and test error per round. So you can see that uh, on the round 10, that you can see that is the last round, the model has less parameters, right? And the test error is smaller too. So at each generation, we can, except for this beautiful here, we decrease the model size, and also we decrease the test error. So the main topics that because I already talked too much, but the main topics that I talked was evolutionary algorithm, right? Language models, prompting, and how to use it. So there is more to that you can do with. It's a new research area combining evolutionary algorithms with language models. Uh, the papers that I present to you guys today is out from this year. So, and there is some older papers, but we'll get the like 2015. So it's not so explored yet. Uh, I think we can improve a lot of our models using language model as crossover and mutations operator. Also, I think we can explore language model when we have a search space. There is not for instance a search space that has double values, float point values, because the search space is huge. And then we can use the language model to kind of try to discover which range we are going to work with. But yeah, of course, that if you're going to change or start to work with language model, I would not say that go to OpenAI and just use their one. I suggest you go to Hugging Face, and if you're working with something related to graph, go on and use a language model that kind of specialist, or like is a professional on graphs. If you are going to use math for math problems, same thing. Go to the Hugging Face and take the model that was training on latex papers, so knows a lot of language of mathematical functions. So yeah, that's it. That is my presentation about evolutionary approach with language models. I highly suggest you guys read the paper. The first one, at least, is very easy to read, and you'll not even see the time pass. But that's it.